Welcome back everyone to the course on topological phases of matter. We were going through the week 1, the chapter 1, which is mathematical foundations of geometry and topology. And let me remind you the instruction, that is that this chapter itself is a full course, but I am trying to squeeze it within one chapter, which means we are skipping a lot of mathematics, but also I am going through faster. So, what you have to do is that you have to slow down and you have to rewind to go back and go through these things slowly, and also fill in the mathematical details if some of you are interested from the book Nakahara. Okay. So, here the purpose is to give you a fundamental understanding of where all this topology, manifold, Berry phase, all these things coming from, Berry connection, all these things coming from. And it comes from a more fundamental mathematical background, which is we are slowly getting into, which is pretty much if you have a topological space, non-trivial topological space, and our Brillouin zone will offer such thing in certain Hamiltonian or with magnetic field. So, how do you get such topological space, and that will give us the Berry phase and quantum Hall effect and so on. So, trying to right now understand what is topological space, manifold and so on in an abstract way. Okay. So, we have the way we set it up is that we start with set, and everything we can start with set, and then if we add structure into sets, then we get different things. And we talked about vector space and groups, in which the all the elements of a set has a closure property under the addition and group composition. And then we switch to topological space, in which we said that there must be a structure among how the different elements of a set are arranged. If you arrange it in certain way, you will get one shape. If you arrange it in a different way, you get another shape. And the way that we give the shape to a set is through topology. And the topology we are interested here is open sets or balls or disk, depending on the dimensions, right. So, we take, if we are giving open sets, and that open sets sort of give you some sort of a continuity between different parts of the set or topological space, all right. And then we had certain properties about how that open set has to follow, and we have gone through that briefly. And then we have gone through map. For any set to any set, there is always a map, and then when you have set with a structure to another set with a structure, then you will have also modifications on the map such that the structure remains preserved. And for topological space, the mapping from one topological space to another topological space is called continuous map, and if that map is bijective, one to one, then we call it homeomorphism. Okay. And then we are talking about how do we quantify each topological space, or under homeomorphism you can go from one topological space to another topological space, and if you can do that, then roughly speaking we will say that they are the same topological space. So, that means the topological property, the geometric property which may arise from a topological space will remain invariant if you go from one topological space to another topological space which are homeomorphic. So, that means you choose your favorite topological space, you compute it, and then you are done with it. You do not have to worry about distorting the shape and all. But if you have another topological space which is distinct from this, then the topological properties will change. So, then how do you distinguish them? And one of the useful way, means the one that becomes physically observable in condensed matter, are through loops, and we said also that there are various loops which are homotopy to each other, and homotopy is an equivalence class. So, that means you can squeeze this loop into a point by continuously deforming this loop. The same thing you can do, and in fact you can go around twice and get a bigger loop, and that loop is same as having one loop because continuously you can deform. Okay, so that is what we are talking about. On the other hand, if I have a different topological space, you see this is the different topological space because this topological space has a hole. So, that means some points of the set are removed, and this topological space is distinguished from this. How do you see that? We see that this loop cannot be contracted to a point because it still have to wrap around or wind around once, whereas these loops you can contract it to one a 0 or point. So, that means at least there are two types of loops, and then if you go around twice, that will be different from going around once, which was not the case here. You go around twice, that is same as going around one or putting it to a point, but here you cannot do that. Okay. So, that means these two loops are not homotopy. And we also talked about that all these loops then form a space called loop space, and this loop space, then if you take each element from each equivalent class of those loops, that forms a group which we call homotopy group. Okay. And we will come back to talk about what is this number means. So, here it is just one means just a line loop. Okay. And you can also show that, which will be homework, that these loops form a group. And then we were taking few examples. Okay. So, so this is a non-trivial topological space, and you will see that this has different set of loops. But let me go back to even a simpler topological space, which is any r real number, and let me take 2. So, that means I have one real number, another real number, and in this case you have all these sorts of points and maybe some topology which is open set that is provided. So, now here I can choose any point called base point and I can draw a loop, and you can see that these are all trivial loops. So, there is only one type of loop which is let us call it gamma and R2 this group has only one element which is this loops, and this loop is nothing but the point, right. Let me denote that point as either P or 0, it is a kind of which means this loop has only one element and generally we denote it by 0. Okay. And so, this is a trivial topology because it does not have any non-trivial loops, just one element of this homotopy group. And now, let us talk about some non-trivial topology. It is very clear that this 1 signifies the dimension of the loop, and here right now we are talking about just a one dimensional loop like this, right. We will talk about two dimensional loop later, and this is the topological space, and here we are talking about S1. So, this blue line is the S1 which is my topological space, and the black lines around it is the loop, this loop. Now, you can see that this topological space has one hole. So, that means you can have this sort of loops. One is like going around like this, which is same as going to a point, and then I can have one more loop which is like winding once, and if I wind twice, that cannot be smoothly deform into going around 1. So, that means going around twice is different from going around 1 and so on. So, that means this loop has 0 element which is like this, and then you will have this thing. So, that means this group is same as or isomorphic to Z, and Z here stands for 0, 1, 2, and that roughly gives you the winding number around this topological space. And then you can do that easily for other topological space, and you can see that this topological space is different from a cylinder which has S1 at every R point, and you can see that this is so actually this is topologically equivalent in this case, in this sense that it also has one hole. So, you can actually squeeze these directions and make it a circle. So, this circle and this cylinder are homeomorphic. They are topologically same, and that signifies from the number of loops you can have. You can have one on the surface and you can go around it, which is this way, and you can go around twice and thrice, which will be all equivalent to this. Okay. And this is in contrast to a torus. So, torus has S1 cross S1, right. So, now you can have a loop that will go like this, and you can have a loop which is like this, that what is drawn, and for every loop you can have one more loop, and that is what Z cross Z means. So, this is topologically distinct. On the other hand, if you think of S2, which is a block sphere or two-dimensional surface, and I am drawing only line loops. Okay. Now, I can see that this loop and even this loop there is no hole. So, that means this entire loop also can be smoothly deformed to a point here, almost like bringing here. Like this, like this, like this, and you can see that smoothly can deform, there is no hole that will encounter. So, that means this also, the one loop on this topological surface gives you 0. Okay. So, this is then topologically distinct from this, and is also distinct from this, whereas this and this are topologically same. Okay. And we will quantify this number towards the end of this chapter. Okay. Now, let us talk about higher dimensional loop, and not so much that you can visually see what is the higher dimensional loop, but let me at least walk you through. So, what do we mean by two loops or two sphere? Okay. So, this is like two loops is kind of S2 if you like. Okay. So, suppose I have some sphere S2, okay, which is my topological space, and earlier here we took that, but we only drew one loop. Now, we are drawing it two loops. So, how are you going to draw it? This is much like making a blanket and wrap it. So, let us say I have some blanket, and then I take all these points and put it together and wrap it around it. Okay. It is like making a momo. So, you take it and wrap it around it, and that is also S2, but that is my loop, two loop, okay, or two sphere, and that is what this thing stands for in the subscript. This is the two loop and this is the topological space. So, now you can see that if you draw two loops on this sphere S2, you get Z2. Okay. You can wrap it once and you can wrap it twice and so on, and you will see that you will get different number. If you wrap it twice, that is different from wrapping it once or unwrapping it. So that is why you will get Z. Okay. And then if you do the same thing for torus, so if I do a 2 loop, then we see that Z. Okay. Whereas if I draw 1 loop on a torus, we got Z cross Z. So that means even on a given same topological surface, you can have multiple topological invariants, and that is completely fine. Okay. So if I draw 1 loop, I will get this, and if we get this 2 loops, that will be, it is like a surface integral over this entire thing, whereas the first one was line integral. So this 1 loop, we will identify this to be related to winding number, whereas 2 loops is like a surface integral, we will identify that to be associated with Chern number. So these things will identify to be equal to Chern number. Okay. So now remember, when you have a higher dimensional sphere and you draw a low dimensional loop, we got a trivial loop, right, at 0. And here these are visually difficult to see, but it sort of works. So if I have a S3 and doing a S2 loop around it, you will always get 0. Okay. And you can then modify this to n loop on various topological space, like 3-dimensional winding number, 4-dimensional Chern number, 5-dimensional winding number, 6-dimensional Chern number. So even dimensions, you will have a surface like integral, which are called Chern number, and odd dimensions you will have a volume like integral, line integral and volume integral, which are called winding number. We will see those things. Okay. And also the loop that we are talking about, it is like you take the n-dimensional Rn, and you take the surface. So this is some sort of a n-dimensional R, and then you take one less dimensions, which is the boundary. Okay, R1, and you wrap it. You identify all points of the boundary. Okay, and that is how we get a n-1 dimensional loop. Okay. We will not go further into in details of this, but this is a side remark of how n-1 dimensional loops are generated. Okay. And let me just show you quickly, and as we said that if you have n-dimensional loop on a n-dimensional sphere, you always get Z, because it is kind of a wrapping the surface with the same surface. You see that? Okay. You see that the diagonal elements you always get Z. And the lower one we already talked about. If I have a S2 surface and if I draw a 1-dimensional loop, you will get 0, and that works for any higher dimensional. So if I have S6 and I do pi 3, pi 4, pi 5, all of them will be 0, and only pi 6 on S6 will be 1. And if you go to the other directions, it becomes more complicated, and we will see that through symmetry. For example, time reversal symmetry, how that allows you Z2, Z2 and so on. We will see that not in this chapter, but in the future. Okay. So, one more quick thing we have to define called functions. So, as I said, the topological space is abstract. We just define it to be a set with some topology. We did not put anything else. And then after that we define a curve or point, right? It is some point. Now, if on this point, if I want to define a function, and we will use that function or map to define many things, including manifold and all. How it is defined? It is just a map to R, because we want to deal with real numbers eventually to be able to make things measurable. So, we have to define things which are measurable, and measurable quantities are defined in R. So, we have to define things on the manifold, and the trivial one, the simpler one is of course functions, and then we will learn how to define vectors, tensors slowly. The first, and how you define is just a function, okay, just a function which takes you from the topological space to R for every point to a function which is a real number. Now, I had a curve which goes from some interval, and interval we still have not defined, but roughly speaking it's like some time interval, initial time to final time, or various other parameter space. The bird is flowing from one tree to another tree, that is also interval and you had a curve, and on this curve we want to define some functions, right. For example, density on this particle or momentum, things like that we want to define, and this is how it is defined. And so, these are like a composition of two functions, two maps, we have learned that, and this is how the mathematically it is written. And generally we are more familiar to look at it like that. So, assume that this is R which defines your curve, and then we define some functions, some density, and that is how it will be done. So, it is like taking the interval and drawing a curve on your R. Okay. And we will use this now to define manifolds and other things. So, manifold is a topological space, but with some restrictions. So, all manifolds are topological space, but not all topological space are manifolds. And I will give a counter example where some topological space are not manifold. But what happened is that everything that is physical and all the physical activities in this universe happens in a manifold. This was the claim by Einstein when he was developing general theory of relativity. Let me give you a punchline about manifold, or kind of an intuitive way to remember, and which I am calling slogan, is that a topological space in which we can define a coordinate, or you can even say that the topological space which we can coordinatize, and we need a coordinate system to define all our mathematical formulas. So, that means the topological space in which we can define at least a local coordinate, that is very important. I can have a curved space and I do not have a global coordinate, but I still should be able to define a local coordinate. If you cannot do that, that is not a manifold, but if you can do, that is a manifold. So, the topological space that we can coordinatize is a manifold. Okay. Now, let us look at the rigorous definition which is written here. A topological space, and here it is X, now I am calling it M, is the set with Tm is the topology, is a d-dimensional topological manifold. It's all manifolds are topological manifold. So, we do not eventually call it a topological manifold, we just simply call it manifold. If at every point on the manifold, on the topological space, and generally we talk about a standard topology. So, that means there is an open set or open neighborhood. At every point in a open neighborhood, every point, I will have a homeomorphism, I will have a map which will take me from this topological space locally to RD. This is very important. It has to be RD, not a homeomorphism to any other manifold or topological space, it has to be a RD. RD is a trivial one, but here we are doing it locally. So, even if you have a non-trivial curved manifold, at least locally we should be able to define d number of variables, which we will call tuples. Okay. And mathematically, so at every point within that open set, which is a part of a topology, I should be able to map it to a number or a d numbers, which will also be a part of a open neighborhood in RD, and I will show you the picture in the next slide. And these are the image in RD, and there will be then d number of these variables, and we are deliberately using the notation x to remind you that this is kind of like your coordinates, okay, denoted by xt is an order d tuples on RD. Okay. And here is the picture. So, suppose this is my topological space, okay, and I have some P1 is my point at which I want to define a homeomorphism or coordinate to RD, and RD will always have a standard topology, which is also kind of an open set. It is a flat open set, and this is the open set, and this is the image of the open sets. So, now this x, there must exist an x, and that is a homeomorphism. So, that means we can also go back, it is a bijective. So, that all points can be mapped to locally to this open neighborhood here, and I sort of like to denote it like a coordinate system. Although we will learn the coordinate system later, this is actually not a coordinate system, although I sort of drawn it as a Cartesian coordinate, but do not take it literally. This is just to remind you that it is roughly speaking we should be able to get x number of variables, d number of variables. And then at another point I do not necessarily be able to map it to the same one, because it can be a carved one, right. So, if I have a carved one, I should, so the definition says that I do not necessarily have to go to the same RD, but I should be able to define an RD which may or may not be the same as this. If it is same, then it is kind of a flat between these two region at least, but it might be a different one. For example, this can be a Cartesian coordinate x, y, z and so on, and this can be a spherical coordinate theta, phi, r, and or even cylindrical and things like that, or even these two can be rotated to each other. So, at least at every such open set I should be able to map it to RD. This is what the topology says. But there is one catch that you have to because we know that the union of two topology is also a topology, and there will be an intersection, and at this intersection, like if I take a point, if two different maps are defined x and y, they at least one should be able to go from one to another, because the map has to be unique. The coordinate system at a given point must be unique, right. Which means even if I define this x and y differently for these two open sets, there must be a transition map which can take from all these points into this one. So, if I have defined in this case I defined a Cartesian coordinate, in this case I defined a spherical coordinate, I should be able to go from Cartesian to spherical coordinate. So, that means this map, the Jacobian, must exist, and the composition of map is generally written like this. So, T is, if I am calling T going from here to here, I can also define it as if I first go this way and then goes this way, right. So, here going this way means x inverse after y, okay. Mathematically speaking, this is how it is written. So, a transition map also has to be present for a topology, for a manifold. Okay. So, there are few nomenclature. So, what we have done is that let us take this example or let me just give you the nomenclature first, and then I will give you the example where this comes from. So, then a topology, a manifold is more than a topological space in which for every topology there should be a map to there should be a homeomorphism map to RD. So, and each of these map is called chart. Okay. And then a manifold must be made of a union of all these charts, which is like an atlas, and charts are like this flat coordinate system, if you like. Okay. And I should be able to combine all these charts and get the manifold in RD, and that is called atlas. So, that means a manifold consists of three things now, the topological space and an atlas. So, manifold is 3 and topological space is 2. Okay. And there should also be a transition map which between different neighborhoods. Okay. It is also homeomorphic RD to RD, that also has to be there. So, the name comes from here. So, let us say I have the earth map, I want to draw an earth map. So, I can draw it like this, I can make it small and I get this globe that you can buy. But then if you go to a bookstore and you do not want to carry a globe, so what you do is that you want to get a book, and in this book what you do is that you take these small curved open sets and make it each one into one page, and that is, so this one will be drawn in a page, and that is chart. And then in one page you will have only one region, in another page you will have another region, and if you take all these pages, that is called atlas. So, if you actually go to a library and ask for a atlas, that is what they will give you, a map of the earth in pages. Okay. So, that is where the name came from. Alright. So, today we will stop here and then we will come back to talk about the examples of manifold.